Hello everyone, welcome to this session. Today I'll be highlighting the 8 main components you need, to build a fault-tolerant infrastructure in the cloud, specifically AWS. They are DNS, load balancing, compute resilience, database high availability, caching, storage redundancy, network isolation, and monitoring. Okay, so I'm going to go down the list and just explain how these 8 components work together, when configured properly to build a fault tolerant infrastructure. And when we talk about fault tolerance, what are we specifically talking about? We're talking about eliminating single points of failure. Sometimes, a service can go down, or a database can go down, or a server can become unavailable, but that shouldn't affect the day-to-day of our customers or whoever is using the applications and things of that nature. So we're going to build a fault tolerant infrastructure. And we just go down the list, right? And start off with DNS. So when we talk about DNS, what are we talking about? What is DNS? DNS acts like a translator for human readable domain names, like say an Amazon.com. Translates this to an IP so that the computer can understand. Now, what this means is without DNS, we cannot access our applications, we cannot access our databases or anything of that nature. So we have to make sure that DNS is always available, right? And how do we make DNS to always be available or highly available? AWS has a service called Route 53, which does exactly that, okay? Route 53 does this by, first of all, doing health checks, frequent health checks, to make sure that the DNS servers are working properly. Then it also has multiple DNS servers. So maybe it's 1, 2, 3, 4, 5. So if one server goes down, the other servers can handle the load just fine. There's also global distribution, spanning many geographical regions. So if there's a natural disaster in one geographical region, the other ones will be just fine. And then it also routes traffic away from failed regions. So, if server 1 was working just fine yesterday and it goes down, Route 53 is smart enough to know, okay, don't route anything that way anymore. Do 2, 3, 4, things like that. So by doing that, we have a highly available DNS system setup. But if we want to take it up a notch to a level of, fault tolerance, then we also need like secondary and tertiary DNS services. So right now we're using Route 53 as the main one. We will probably need to use Google Cloud. We use Google Cloud, and we could also use maybe Cloudflare, right? So that way, if Route 53 is unavailable, Google Cloud can step in, or Cloudflare, we have those to fall back on. So that's building a robust architecture at DNS level. So next on the list is the application load balancer, or load balancer. Okay, what is a load balancer? Load balancer acts basically like a traffic director at an intersection, routing traffic to different roads so the traffic moves with ease, right? Same concept is applied here. We want the application load balancer to be able to route traffic evenly to the different servers that we have, because if one server is overloaded, it could crash. So in order to build a fault tolerant environment, we definitely need an application load balancer that will route traffic between the different components. Now, it also does a few extra things, like automatically removes unhealthy targets, distribute load across availability zones. So if one AZ goes down, the other AZ can pick up. Even recently, the ALB will handle things like encryption and decryption work, so the servers don't have to, And then for like a fault tolerant environment, it would do health checks every 15 to 30 seconds, automatic target deregistration, like we already mentioned, and then there's also built-in like protection against malicious traffic loads and things of that nature. So that would be the load balancer, right? We spoke about DNS load balancing, so now we're going to go into compute resilience. Okay, compute resilience. When we talk about compute resilience, we're really talking about your auto-scaling groups. Okay, you have to configure great auto-scaling groups, right? So you have the right amount of resources at any point in time. You have peak hours, off-peak hours. Think about it like a restaurant. In a restaurant, you want the right amount of servers, at peak hours. You might need 20 at one point. You might need 2 at a certain point. Okay, so you have to design your auto-scaling groups to be able to do that. And then also, so it's very proactive, but also reactive. It's like you put this in place so that when you have peak hours, you have the right amount of servers and so forth. But in a situation where you have a server go down because of some geographical occurrence, right? What happens? You have to be able to generate a new server, bring up a new server in a timely fashion. So the way this generally works is that you would have your auto scaling group set up such that you're using spanning maybe 3 availability zones. Okay, your ability to be able to scale up and scale down as necessary with workloads, and your ability to be able to repair as well. So that's very important. That's what your compute resilience entails. So in order to build a fault-tolerant environment, you need to configure auto-scaling groups correctly and properly. Yeah, and that should cover that. The next thing on the list would be databases, right? Now, in order to build a fault-tolerant environment, minimum you need your database to be in. You need to have a multi-AZ deployment, okay, which entails synchronous replication between the primary and the standby. Okay, so before a commit is issued on the primary, the transactions are written on the standby so that it's synchronous. At any point in time, if the primary goes down, then the standby is going to be available. Now, this constitutes a high availability configuration. You want it to be fault tolerant, you need to add read replicas as well. Okay, you need to add read replicas. Read replicas at every given point in time handle read loads, but if the primary, the right instance goes down, the primary goes down, a read replica can be promoted to primary as soon as possible. Okay, and then also you will have to add some type of retry logic at the level of the applications, such that if the primary goes down and you're bringing up and the read replica is getting promoted, the retry logic would queue the user's request and route it to the read replica after it has been promoted, or to the standby, whichever happens first. So if you configure this correctly, then the user shouldn't experience any issues, or very minimal issues, right? So that would be a fault-tolerant configuration for the databases. Now, the next on the list would be the caching layer. Okay. Now, the caching layer could be one of 2 components. It could either be Redis in AWS, could either be Redis or memcache. Okay. Now, Redis is the recommended approach because it has a more complex and robust infrastructure, right? So it can store complex data. It has built-in replication and failover. It can also persist data to disk, which means that it could have longer storage times, and then also it's more fault tolerant. Now, memcache is more basic in nature. It's faster for basic operations. It has no built-in replication, and it's less fault tolerant. So if you are just trying to build something that is highly available, you can do memcache. But if you want a fault tolerant, you should probably go with Redis. Okay. Now, what's the purpose of ElastiCache? ElastiCache is in-memory cache, right? It's in-memory. So basically, it's super fast memory storage that sits between your application and your database. Think of it like keeping frequently used items like on your desk, instead of having them in a filing cabinet somewhere, such that if you need them, you can grab them. So it basically functions like the memory layer in a database, but it's just bigger, stronger, and better, right? More robust. and you can store a lot more data, and it's faster. So it prevents. So it's great because during like a failover or situation where database requests are being queued, when the new database gets promoted, all that load doesn't just hit the database. At least 80% of that is served at the level of the caching layer, and only 20% of those go to the database. So that allows the database, the transition, to be smoother, right? And we don't have a second crash because of that weight. So it's very essential to have caching in place, especially Redis. Okay. So yeah, that would be. And what is the next one? I believe storage redundancy. Okay. Now for storage redundancy, really we're talking about S3. Okay. It all boils down to S3. You have to configure your storage such that everything replicates to S3. Even at the level of the database, at the level of EC2 instances with EBS volumes, everything gets replicated to S3. The more robust you make it, the more AZs you include, the more regions you include, the more the more durable your storage is. The more robust it is. So it's about how much are you willing to spend. You could do you could use S3 at the level of the AZs. You can configure cross-region replication such that if one region is affected, your data is going to be in another region. So it's really about utilizing S3 in the most robust way possible. It also depends on how much money you're willing to spend, right? So for like a fault tolerance setup, you would have like S3 versioning enabled. Okay, you would have RAID configuration for EBS volumes, and then maybe hourly snapshots. You have to put hourly snapshots in place, and then also you have pre-created volumes in multiple AZs, things like that. So it's really about how can I eliminate single points of failure? How can I make sure that recovery is faster? Things like that. But everything is really centered around S3. So that's for storage redundancy. And then also, probably the most important, network isolation. Okay. Network isolation is really how you configure your network in the VPC, right? So think of VPC like designing a secure office building with different floors and security levels, right? So the lobby will be where your public subnet is, where multiple visitors can access, and then there'll be like an employee floor, which is in the private quarters, which is employees only, and then there'll be like a server room, which is like only the highest top security can enter, which would be like the where you house the database. So being able to segregate this the right way is important for having a robust architecture. Okay, so your internet gateways will have to sit in the public subnet. Okay, and then your applications, web servers and everything, private subnets, and your databases as well. Now for applications that need to access the internet in order to download updates and things of that nature, they'll have to use a NAT gateway. So there'll be communication from the NAT gateway to the subnet where the internet gateway resides. So you really have to build that infrastructure in such a way that nothing has access to the internet which shouldn't, and anything that has access to the internet has to be in the public subnet, and the public subnet has to be isolated such that anything coming to the public subnet cannot access the components which are in the private subnet. So it's really making it robust enough where there's that separation and security is like prime. Okay, so that's really how that configuration is supposed to look like. So you go from the internet whereas where users are, to the public subnet where the load balancer is, to the private subnet where the app servers is, and then the database subnet where the databases reside. And then last but not the least is monitoring and alerting. This involves, having Lambda functions, CloudWatch, whatever metrics that you use to proactively monitor the database and take action without user intervention, right? It's like if this is happening, um, for every single component that we have gone through, monitoring plays a big factor. How does the auto scaling group know to provision another instance? You have to set a threshold. Oh, at 70% load, I want you to do this. If this happens, I want you to do that. And all of that is centered around monitoring, because you have to monitor to know. So you also have to add extra monitoring capabilities and things in place, not just like default AWS monitoring, but you have to put some monitoring in place and alerting, so you know what's going on, and then you can proactively handle those situations. So yeah, that's pretty much it. We've covered basically DNS, load balancing, compute resilience, database high availability, caching, which was Redis, storage redundancy, which is S3, network isolation, knowing how to configure your subnets correctly, and what to put in what subnet, where your NAT gateway should go, your internet gateway should go, your network servers, application servers, database, and so forth, and then monitoring and alerting. So if you check off all these boxes, then you should have a fault tolerant infrastructure in the cloud.